Grade 12s, here is a quick grade 11 trig recap. The most important thing when it comes to trig, the thing that I want you to draw on every single page of your trigonometry work is the cast diagram. You guessed it. We have a y-axis, we have an x-axis, we have Sokotoa, some old hens cackle and howl till old age. Or what I haven't included in this PowerPoint is sine is y over r, cos is x over r, and tan is y over x. And those values on the cast diagram on the Cartesian plane, where y is positive and where x is positive and where y is negative and where x is negative, that determines y, where each trigonometric function is positive or negative. So we have the all quadrant. That's because cos, tan, and sine are always positive in this first quadrant. The first quadrant is between 0 and 90 degrees, and there are other names for this quadrant, which I'll get to in a little while. Why is everything positive here? Because the y values are positive in this quadrant and the x values are positive in this quadrant. So no matter what y or x value you substitute into these three trig ratios, the ratio will simplify to be a positive number. Right. This is the sine quadrant because only sine will be positive as a ratio in this quadrant because y is positive and sine is y over r, the opposite over hypotenuse. Hypotenuse is always positive. Tan, which is y over x, would be y over x would be negative. That's why tan would be negative in this quadrant. Likewise for cos. Cos would be x over r. Since we're on the negative half of the x-axis, cos would be negative in quadrant 2 as well. I've failed to label this as quadrant 1, 2, 3, and 4, but I expect you to do so when you make your notes. Okay. Not that we ever really refer to it. We usually refer to them as the all, sine, tan, or cos quadrant. Then we get the tan quadrant because tan is the only trig function that's always positive in this quadrant. And then we get the cos quadrant because cos is the only function that's always positive in this quadrant number 4. Now, each of these quadrants have other names as well. And that is, in quadrant 1, I can call this the theta quadrant because if you have an acute angle, theta is always an acute angle in trigonometry, by the way. We always work with acute angles. Why? Because trigonometry stems from triangles, and most triangles have, right angle triangles. That's where Sokotoa comes from. And right angle triangles will always have acute angles. So that's why every time you see a theta in this cast diagram, know that that theta is an acute angle, 100%. So quadrant 1 is the all quadrant, or it's the theta quadrant. It's also called the 360 plus theta quadrant. So if you see a really big angle, you know that you can just write it in terms of 360 and an acute angle. Another name for quadrant 1 is the 90 minus theta quadrant. So in this quadrant, you have anything smaller than 90 degrees, hence we can call this the 90 minus an acute angle quadrant. I'm not going to explain every single one, but there you can see that in quadrant 2 we've increased our angle to be above 90 degrees. So this is the 90 plus theta quadrant, or it's just a bit smaller than 180 degrees, so it's the 180 minus theta quadrant. Once you're in quadrant 3, we can call this quadrant 3 the tan quadrant, or it's the 180 plus theta quadrant, or it's the 270 degrees minus theta, because you can see that 3/4 of 360 will give you 270 degrees. If you want to be a little bit smaller than that, it's 270, take away a theta. Then once we enter quadrant 4, we enter the 270 plus quadrant, and another name for this is the negative theta quadrant, or potentially even the 360 minus theta quadrant. Okay, so I like to call these little things other names for the quadrants, or even outfits. Like it's one angle, but it can be represented in 3 different ways, and so it's as if the same person, but you're changing outfits. You're getting dressed up and you're changing clothing. Same thing underneath it all, but just different appearances. Now, these outfits or names of quadrants that are typed up in black link up to what we call the reduction formula. Now, a reduction formula, where does the word reduction come from? Well, it comes from the idea of being able to reduce a big angle, to reduce an angle that lies in one of these quadrants to the trig ratio of just a small little acute angle all by itself. So we can reduce something like 180 minus theta to be just theta. But when we do that, we have to take care. We've got to be careful of the sign of the trig ratio in the specific quadrant we're dealing in. So, for example, if you are given 180 minus theta, and you need to express it in terms of one little trig ratio, or you need to reduce this or simplify it, you go to this quadrant. Go through the degrees. Where would 180 minus be? Ta-ta, right there in quadrant 2, which belongs to sine. So nobody else other than sine can be positive in this quadrant. So when you see 180 minus, you're allowed to reduce it straight away and replace cos 180 minus with cos theta. But then just go double check. Is cos positive or negative in the 180 minus quadrant? That's sine's quadrant, so cos will indeed be negative. Okay, then the second example is just to throw you in the deep end, to trick you, to test you, to see if you know your stuff, and I know that you do. Whenever you are given a really negative angle, look at how what's in this bracket doesn't link up to any one of our black reduction formulae figures over here. But we can manipulate it such that it does match one of these. Negative 180 degrees, it's as if you're starting on your x-axis and you're going in a clockwise direction by negative 180 degrees. If you were to merely add 360 degrees to that, do you agree you'd end up in the exact same spot? So we are allowed to add 360 degrees to any angle at any time you like ever. Then in order to make it workable, in order to guarantee that the angle falls on this cast diagram. So we add 360 to negative 180 degrees and we end up with positive 180 degrees. Now we're sitting with negative theta plus 180 degrees. If you just swap these two round, you'll see that you end up with 180 degrees minus theta. Now, I was quite silly and I didn't complete this, so I'm going to ask you to please complete this. Pop in another equal sign over here if you want to take these notes down. Otherwise, just realize that this example right here is incomplete because I haven't reduced it. I just manipulated it and then I completely forgot to reduce it, and I'm already 8 minutes into this video, so I don't want to go back now. So this 180 minus quadrant is right over here, so we can write this as sine of theta. What is the sign of sine in this quadrant? It's positive, so this over here can be equal to sine theta. Rightio. These in red link up to what we call the COCO rule, which is actually just the cofunction rule. Cofunctions are only ever used for cos and sine. Never, 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 never write tan in terms of 90 plus or minus or 270 plus or minus. Tan is a no-no for the cofunction rules because sine and cosine, the cofunction of sine, cos, are cofunctions, and they are the ones that differ by 90 degrees. I'm sure you can remember last year, if you shifted your sine graph over by 90 degrees, you'd end up with the cosine graph and vice versa. So if you see a cos and a 90, you immediately write down sine. If you see a sine and a 90, you immediately write down cos. They must change into each other. See how in the reduction formula, cos stayed cos, sine stayed sine. But in a co-function rule, cos becomes sine. All right, so if you see cos of 90 plus, immediately write sine theta. Okay, but now the sign of your answer is the sign of the original function in that specific quadrant. So in the 90 plus quadrant, the original function on the left-hand side of the equal sign, cos, is negative. It's negative in this 90 plus quadrant. So even though we've changed it to sine, and sine is positive in that specific quadrant, the original function cos was negative, and that's why the negative is on the right-hand side of the equal sign. Okay, again, for cos of 630 plus theta, this does not fall within our interval. It doesn't fall within our cast diagram that only covers 360 degrees. So we've got to manipulate this bad boy. If we take 360 degrees away from 630, we are dealing with the exact same angle. It's just a revolution earlier. So 630 minus 360 gives us 270, and voila, we are working with co-functions again. So you see a cos, you see a 270, you write down sine theta straight away. Then you double check, okay, what was the sign of cos, the original function, in this specific quadrant? Well, that quadrant is cos's quadrant indeed, so it is a positive sine theta at the end. Right, not last but not least, I'm just recapping the general solution formulae. And what I want you to realize here is that I'm being a little bit repetitive in using theta. I would have preferred to have said x, because these thetas are not these thetas, okay? This is if you're solving for an angle and then you pressed shift on your calculator to get a reference angle. That reference angle is actually this theta in this cast diagram, okay? So basically what I'm saying is that if you're solving for an angle and you had cos all by itself, you press shift to get a reference angle. And then your two options for the size of the angle for which you're solving will be plus minus your reference angle plus K360. Why are we adding 360 degrees? Because we know the cosine function repeats itself every 360 degrees. The period is 360 degrees. And why is K an element of integers? Because we're talking about full repetitions, the full curve of the graph. In other words, we're ruling out the chance of having fractions. So K needs to be an integer, and always write K as an element of Z every single time you do a general solution. Okay, why do we have plus minus the reference angle? Because if you look back to the cast diagram, those are the quadrants in which cos is positive. So the plus theta quadrant and the minus theta quadrants. Hence, we have plus minus our reference angle. Then if you look at sine, if you're solving for x or an angle and you're trying to find the size of that angle, you need to get sine x on its own, then you press shift on your calculator to get a reference angle. Then the possible sizes of that angle will be the reference angle plus K360 or 180 minus the reference angle, because the reference angle is quadrant 1 and 180 minus the reference angle is quadrant 2, and those two quadrants are the quadrants in which sine is positive. Hence, we have this type of formula right here. Again, we say plus K360 because the period of sine is 360 degrees. Then we end up with tangent, the tan graph. If we are looking for a specific x value when we've been given a ratio, in other words, we've been given a y value, we get tan of that value on its own. We press shift on the calculator to get a reference angle, and then we say this angle will repeat itself every 180 degrees. So the tan one is easy to remember because there's no two options. It's just one little formula. Cosine has two formulae, even though we've represented it in one line. Sine has two formulae, and tan has just one. Actually, tan does have 2, but let's have a look. Why is this good enough to just say one of them? Because reference angle is quadrant 1, and then plus 180 degrees later ends up in quadrant 3. And so by saying plus K180, we are accounting for that second option in the 180 plus reference angle quadrant. If you were to write it out twice, you'd still get full marks. You'd just be repeating yourself, which is a little bit, what's the word? A silly billy? Nothing. No, it's not a train smash. Anyway, so that's a quick revision of grade 11 trig. Good luck for exercise 4.1 on page 130. I'm sure you might have to read the examples before page 130, but do so because it will stand you in good stead. This textbook from page 129